All right, so this is the form of the ideal gas law you need to know. And then you can look up your gas constant anytime you need to from your test references.
Yeah.
All right?
Yeah.
Now, there are going to be some versions of the ideal gas law that will look a little bit different that we are going to learn how to use, okay? So even though this is the classical version of it, there are some other versions of the ideal gas law, and I think all those are in your test references in that section I asked you to look at yesterday. Okay? So let's see.
All right.
This is a version of the ideal gas law. We had that right here, okay? There it is. PV equals nRT. This is also a version of the ideal gas law right here.
How?
Well, we'll get to that. And so is this one.
Is that density?
This is D here is density, and this is molar weight or molar mass.
Oh, same thing.
You can use the ideal gas law to actually find the molar mass of a gas, which can help you identify what an unknown gas is. Okay? Now, technically, this is also a version of the ideal gas law. Okay? But it just turns out that when you get your gas at standard temperature and pressure, that we cancel out some stuff. So that molar weight divided by molar volume equals the density of the gas. So that's a really simple calculation you can use, but only when the gas is at standard temperature and pressure. Okay? All right. Bill, you probably need to give a little more focus to what we're doing. Okay? And I called you out on the recording here. Okay? All right?
Your mom.
Okay. That's right.
Folks, if you can't hear me, I'm in the back today.
Yes, well, that's not your assigned seat.
But I wrote my name on it.
I don't care. You're absent today.
No, I'm right here.
Oh, no. You're assigned here, and
No, I'm here, right here. It's me.
Yeah, get up on your little feet over here and walk around and sit in your seat.
I will in a second. I got to write my notes. Let's finish our notes real quick. If a
The sample of gas was strangled, suffocated, right?
If a sample of gas has a volume,
That's right. It should be has.
You were so friendly yesterday.
I'm just kidding. Is under a pressure.
2.57.
It's a 4. This is up.
All right, folks. Have you finished writing down the problem?
no sir.
Up, right, right now.
I'm at and has a. I'm at temperature.
You know, they have a step team here.
I'm just like, when you write.
Okay, here I'm being a little bit sarcastic. Quit with the sound effects, okay?
Why are you so sarcastic? I'm always serious.
I've asked you to stop with all that today, okay? You've had enough of the playing around and throwing stuff
You're
and
right.
sound effects. Let's focus on the chemistry, okay? Listen, I want you to have fun, but here's what happens. When you're focused more on making jokes and playing around.
Playing around.
You're not following this.
I know.
Call 'em out on
I gotta
camera.
stop.
And you in particular
Me? Just me?
need to focus on this.
Focus.
Okay?
Right.
All right?
Alright. But you know how when you're writing, you get in a rhythm? I was fine.
Okay, but just please do the work.
You know? Yeah, I am.
All right. Everybody who's finished writing the problem down, you should be able to start identifying your knowns and your unknown.
No.
Alright. So
I may have to help you with a little bit of that once you write your knowns and unknowns, but we'll see.
pressure.
You can reverse these two.
Say what?
So, you want us to use the equation on the left or the equation on the right, or does it matter?
Well, this one really doesn't help you a lot. You could use this, that's fine, but this is the classic version of it.
Don't
Either
you have to
version works.
transfer the Celsius to Kelvin?
Absolutely.
Every time.
So
You
should we
cannot
do that-
use temperature in Celsius.
Should we do that before we list the temperature, or?
You have to show your work, so it really doesn't matter. You can do if you do it, just make sure you show me your work.
What's the number again?
273.15.
What's the gas constant?
It's right here on your test references.
Oh, I got those.
So there's one of our knowns. Okay?
Pressure.
Here's another known. I even tell you what it is.
It's on two, guys. Go. Whatever you do.
All right, so temperature we have here is 25.0 degrees C.
Then you gotta add 273.15.
298.15, but that rounds off to
298.2.
well, I should say that's actually equal. Okay. All right, so that we have those three values here listed as knowns. The question is asking how many moles. So we know we have an unknown
Lowercase n.
of N. We don't know what that is. By having this variable, this known, and this known, and this unknown, I know I need to have an equation that includes all of those. And the only equation I know of that includes all of those also has R. But R is given to you. Okay, all you have to do is figure out, well, which version do I use? All you have to do is match the units of measurement. Match the units of measurement. So, we need liters, torr, Kelvin. Now that's liters, atmosphere, and Kelvin.
No, we won't need
That won't work. Liters, millimeters of mercury. No, that didn't work. Here's liters, torr, Kelvin, and moles.
So you use 62. Or,
So that's the version of R we're going to use.
yeah.
62.37 liters, torr, Kelvin, moles. Okay? That's the version of R we're going to use. Alright, so we're going to write our ideal gas law, because that's going to fit all this. PV equals nRT. Okay?
So how did you get the constant? Hang on.
Chill.
We match the units of measurement with the units of measurement we have in the problem.
Hang on, let me look at my.
So the unit we have liters, torr, Kelvin, and we need moles. Okay? So we need a version of R that has those same variables, or those same units of measurement. This is the one that has matching units of measurement, liters, torr, Kelvin, moles. Okay? All right. Now, at this point, I can choose one of two methods of solution here. I can choose to rearrange the equation so that N is by itself now, before I even start plugging in my knowns. Or I can plug in the knowns and isolate the unknown.
Which would be harder.
I prefer to rearrange the equation first, but that's up to you guys. It doesn't matter to me how you do it. I will give you all credit for either version.
I'll probably do it that way.
What? Plug in first or rearrange first?
Rearrange.
All right. Since I know that N is what I want to find, what I have to do to isolate N by itself is to isolate it in this fashion then. Okay? That allows me to cancel RT on this side, and it leaves me with an equation that looks like this, where N equals PV over RT. N is what I'm trying to find. So I've isolated it even before I start. Okay? Alright, so let's rewrite the equation then with N equals PV over RT. So pressure is 800.0 torr, and volume is 2.57 liters. Alright, and I'm going to put that over R, which we decided was going to be this version of R, 62.37 liters times torr over Kelvin times moles. And then we're also going to multiply that by temperature here on the bottom. Temperature, we have to use 298.2 K. Alright? So this is something that you've probably learned in a math class in elementary school. It was called a complex fraction. Okay? Or maybe it was middle school. I'm trying to remember when my sons learned it. Seems to me it was like 5th grade. They started working with complex fractions in 5th grade. The way you solve the way you do the math for a complex fraction, it's called different things. What I was taught to call it was to invert and multiply. That was the process we were taught. But before we can invert and multiply, we need to change a couple of these so that we have the same kinds of fractions in the entire equation. So we need to have this over 1, doesn't change the amount. Put this over 1 and this over 1. Okay, so what I have is a series of fractions. And what I'm going to do is rearrange the equation in this fashion. I'm going to say 800.0 torr over 1 times 2.57 liters over 1 times, and here's where we invert and multiply. You invert what's on the bottom. Numerator, denominator. The denominator gets inverted and multiplied. So we're going to turn it upside down but multiply it. So Kelvin times moles goes on the top. 62.37 liters and torr go on the bottom. And then this also gets inverted, 1 over 298.2 K. All right? You're about to see one. Okay? All right. Notice if I solve it in this fashion, and this is a perfectly acceptable mathematical way of solving this problem. Torr cancels. Liters cancel. Kelvins cancel. And look what's left. It matches what I'm looking for. What? Excuse me. Alright. So now all we have to do is the math. Alright? All we have to do is the math. Get out that old calculator. You got 800 times 2.57. Hit enter. Then hit your divide button and put in what's on the bottom. Each of these on the bottom going separately. 62.37 and hit enter. 298.2 and hit enter. And your final answer. Wait a minute, I've done something wrong here. Let me do it again. I hit a button wrong again. 800 times 2.57, enter, divided by 62.37, enter, divided by 298.2, enter. Okay. And the number of moles I get, 0.1105451586. Okay? And then we want to keep the units we have left, moles. We want to round off to the correct number of significant digits. These are all, well, this, and this are measured numbers. This is a calculated number. You could say that's a calculated number because we calculated the Kelvin from the degree C. So those are the four numbers we're going to use for figuring out significant digits. This has the least digit right here, 3 digits. So the leading zeros are not significant. First significant digit, 1, 2, 3. We're going to underline from there over. Draw an arrow. And the answer we're going to leave ourselves with is that N equals 0.111 moles. Okay?
You gotta box it. Box.
Yes.
Box, box, box.
Okay? And there's your final answer.
I knew it.